All right, in 8.2, we are going to do like we have done in a lot of other chapters. We'll learn about a new function. We just learned about inverse variation functions, and we're going to start graphing them. We did that with parabolas and polynomials, and lines, all those guys. So now when you graph this here, that y equals 1 over x, first of all, this is the most basic of inverse variation functions. It's called the parent function. We've talked about this before. You take the parent function, you make slight changes to it, and you see how it changes the graph. Now this graph, its shape, has been given a name, and its name is a hyperbola. Not to be confused with hyperbole, which is a completely different thing. This is a hyperbola. This double swooping curve thing, right? That's what a hyperbola is. We're going to talk about some different features of this graph, and what I really want you to get out of this intro is why does this graph look the way that it does? The book concentrates on that it just does. It just does look like that. But I want you to think about it for a few more seconds than that and think, why does it look like that? And if you have it make sense to yourself, you will be in much better shape. I make that case all the time. So let's look at this graph. This is the y-axis. This is the x-axis. Let's look at the shape of this curve and wonder why when we graph this does it look like this? Okay, let's just put a little mark right there. Let's start here and just wonder first, why does it start above, like start at relatively bigger values and then just get smaller and smaller and smaller and smaller seemingly forever? Why does that happen? Well, what we're doing is as we move this direction, x is getting bigger. So we're taking bigger and bigger x's and dividing 1. We're always going to take 1 and divide it by that x. So as x gets really large, what kind of values are we going to get for y? Well, let's start a little table of values here. If x is 10, then y is 0.1 or 1/10. If x is 100, you're going to take 1 divided by 100 and you get 0.01, 1/100th. If x is 1000, then x is 0.001. Right? And as x gets larger, y just keeps getting smaller and smaller and smaller. But here's the cool thing. Here's an interesting thing, and it's going to bring up one of the a big word that you're going to want to remember. What's the limit on y, I guess? As x gets really, really big, is there some kind of limit to y? Will y get to the smallest that it can be? So to answer that question, try putting in 1,000,000. Okay, so we've gone through all these stages and we've gotten to 1,000,000. This will be 0.000001. And what if we put in 10 billion? What will happen? Well, it'll just be like a bunch of zeros and then a 1, right? And we'll put in 100 trillion billion, and it'll be a decimal point and a lot of zeros and a 1. Okay, so the thing about that, the thing you'll notice is that y never quite gets down all the way to 0. It just never can, because the only thing we can do to make y into a different number is to divide it. Divide 1 by some number. To divide 1 by a really big number would make y a really small number. So y will never ever completely get to 0. And if we come over here, we can see why it's like a flipped perfect match. It's a mirror image of this shape. As x gets to be a really big, say, negative number, okay, big negative numbers are technically small numbers, but let's say it's a big number, like 1,000,000, and it's negative, a negative 1,000,000. Well, divide 1 by negative 1,000,000, you're going to just get a decimal point with a lot of zeros and then a 1, and that number is going to be negative. Okay, so then y is going to get really close to 0 from the negative side, okay, but never quite get there. So this idea that we'll take 1 and we'll divide it by this bigger and bigger and bigger number x, and then y will never quite get all the way down to 0. We imagine that there's this horizontal line here, and we call it the horizontal asymptote. Okay, don't confuse that with isotope. It's asymptote. Okay, so you'll really impress me if you pronounce that correctly in class. Horizontal asymptote. So as x gets really large, and we divide by a larger and larger number for x, y will get really small, but not so small that it's 0. It just will never quite get to 0. Okay, so let's shade in the part of the graph that we get. We understand why does it get smaller and smaller and smaller, closer and closer to 0. We could put a little mark here. We kind of have explained by the same reasoning why it gets closer and closer and closer to 0 from the negative side. Okay, but now why does it shoot up like this and just go almost vertically at this point at 0? That's an interesting thing. Okay, so that has to do with when x gets really, really tiny, or when the denominator gets really, really tiny. So as x gets really small, what happens to y? Let's create a different table of values with that question in mind. What happens when x is like 1/10? Well, then to get y, we divide 1 by 1 over 10. We'll multiply by the reciprocal. That'll be 1 times 10 over 1. We multiply by the reciprocal, and that'll be 10. If x were 1 over 100, an even smaller number, then we would do 1 divided by 1 over 100. That'd be 1 times 100 over 1, the reciprocal, and that would be 100. So we can see as x gets smaller and smaller, and we divide 1 by a smaller and smaller number, what's happening to y is it's getting bigger and bigger. So divide a number, in this case 1, by a small number, like 1/10 or 1 over 100, or just get as small as you want. The smaller the number that you divide by, the bigger the number you'll get as a result. So as x gets smaller, or in other words, closer and closer to 0, then y gets bigger and bigger and bigger. And there's just no limit on this. The smaller x gets, the bigger y gets. The closer x gets to 0, the bigger y gets. So that explains why it looks this way. Now something else you might notice is that it doesn't look like it ever crosses over the x-axis, or something funky is going on when x is 0. And especially strange, it goes up like this on the positive side, and then when you're on the negative side, it's from way down here, which it's not too hard to grasp. You just think about small negative numbers, negative 1/10, negative 1 over 100, and these will make very large negative numbers, negative 10, negative 100. Okay, but at 0, when we let x be 0, then we're taking 1 and dividing it by 0, which it's kind of hard to make this intuitive, to say 1 divided by 0 just isn't anything. It's not defined. But you can try to imagine that you divide 1 into 0 pieces, and it's just conceptually, there's no way to imagine that you can do that. It's just, there's no definition for it. Right, so this is undefined. So that's why we see this weirdness at x is 0, because when x is 0, we're dividing by 0, and that can't happen. Okay. So, just like there is this horizontal axis where, or horizontal asymptote where y could never get to be to 0, x is not allowed to be equal to 0, and so we call this the vertical asymptote. Okay, so the shape of it, the horizontal and vertical asymptotes, those are the important parts of the parent function. What we'll do in the sample problems is change it up a little bit, make changes to the function, see what happens to maybe the shape or the location of this hyperbola. Okay, but those are the basics of horizontal asymptote, vertical asymptote, and just the shape of the hyperbola. Okay, so thanks for watching.